So I'm repeating once again. In simple leveling, we'll be having one single station and two readings will be taken. One is backside and one is foresight. One precaution what we need to take is the distance from the instrument station to the backside and the distance from the instrument station to the foresight should be equal, so that any error or any inclination in the line of sight will get nullified and whatever readings you're taking on the staff will be 100% perfect. Okay. In differential leveling, we'll be having multiple station points and we'll be having multiple intermediate sites and multiple back sites and multiple foresights. So when the area to be surveyed is long, then we generally go for the differential leveling. Okay. In practice, the leveling which we generally do is differential leveling only. Okay. Then fly leveling. Okay. It is also similar to your differential leveling carried out to check the accuracy of the leveling work. Okay. Just maximizing it. Okay. So fly leveling is like just like differential leveling carried out to check the accuracy of leveling work. In fly leveling, only back sides and foresights are taken. So generally, fly leveling is done to transfer the RL of one point to another point. Suppose I want to establish one reducer level. I want to determine what is the reducer level of the first step of civil engineering block of MBSR Engineering College. Okay. So what can I do? I can start my work at a known elevation which is already fixed by some government authorities or some government agencies. From there, I'll be doing the fly leveling by simply taking a backside and a foresight. I'll be not taking any intermediate sites. Okay? And I'll ensure that the distance of backside and foresight is equal, and I will ensure that more distance is covered in between also. Okay, around 100 meters or 150 meters, I'll be the distance between instrument station to backside maybe 100 to 150 meters, so that the number of the length, more length will be covered within a shorter duration of time. Yeah, the purpose is I want to transfer or I want to establish a new RL from an existing RL. Suppose we have already done earlier from Kachiguda railway station, we have a RL. You can see the platform. On the platform, we'll be having the mean sea level. Okay, the RL of Kachiguda railway platform. We have started work from there and we have established some around 10 benchmarks in our college by the help of fly leveling. So every time we'll establish an instrument, okay, we'll take a backside, then we'll take a foresight. Then again, we'll change the instrument to other position. At the same position of FS, we'll be taking a backside and again we'll be taking a foresight. Like that, every time we'll be changing the instrument and we'll be taking only two readings, backside and foresight. We will not be taking any intermediate sites between that. Okay. So the purpose is to transfer the benchmarks from one point to other point, also to check the accuracy of your leveling work. Okay, whether we have done correctly or not. Okay. And check leveling is also kind of leveling to check the accuracy of the work. It is done at the end of the day's work in the form of a fly leveling to connect the finishing point and the starting point. So sometimes when you're doing some work in between also you'll be taking some points. Okay, so that you want to check if you have done a work for 4 hours, 5 hours, and if you're not sure of the accuracy, then it will be a big problem for important projects. So you need to have some checkpoints in between, so that you can assure yourself that okay, the work or the readings which you are getting through this experiment are correct. Okay, that is the purpose of your check leveling. Okay, and profile leveling or L section, we call it as longitudinal section or profile leveling. Okay, both are synonymous. Okay, so it is used to take the levels along the center line of any alignment like road, railway, or canal. The objective is to determine the undulations of the ground surface along an alignment. So you can see in the adjacent figure. Okay, this is the original ground surface. There is some dirt and dashes. Okay, that is the original ground surface. Okay, and this is the formation level. Okay, this is the level at which I want to lay this my work. Okay, and this is the above one is the finished surface line. Okay, so I will be taking the readings at the centers. Okay, and I'll be calculating what is the reducer levels. I'll be placing my staff at the center along the center line, and I'll be placing what is. I'll just show with another example. So this is my actual ground surface. Okay, so I'll be So this is my RL which I want to establish. Like I want to lay a road line or a railway line at this level. This is my single straight line is my designed RL at which I want to lay my structure. Okay, and this is the natural ground surface. So what we'll be doing is so we'll consider this as the center line. Okay, and at every 5 meters or 10 meters or 20 meters, depending on your okay, depending on the interval which you want, you will be taking the staff readings. So like this. Assume that this is a 10 meter 10-meter interval. So I'll be establishing a center line along this road. Suppose this is my road which I want to, this is the width of the road which I want to lay. Okay, so along the center line of this one, along the center line of this stretch, I'll take establish some points at every 10-meter interval or 20-meter interval, depending on the accuracy and depending on the purpose of the project as well as the cost of the project. Okay, so I'll be establishing my instrument at some position from here or here on any direction from where I'm able to see the, I am able to cover the most of the area. Okay. After I establish my instrument at this, I will do the temporary adjustment, setting up of the instrument, leveling up, and focusing of the eyepiece and objective. I'll do all the temporary adjustments, and I'll take a benchmark. Okay, I'll take a reading on the benchmark, which is going to be my backside. Okay, so this is going to be my backside. This is my instrument position. After I take that backside, then I'll be placing my staff at each of these 10-meter interval. I'll be placing my staff here. I'll be taking what is the reading. I'll be placing my staff here. I'll be taking what is the reading. So at every 10-meter or 20-meter interval, I'll be taking the staff readings only along the center line of the stretch. So this bottom rectangle is my width of the road which I want to lay. So I'll identify where is the center line. Okay, and along the center line, I'll be taking what are the staff readings. Once I take the staff readings using the height of instrument method or rise and fall method, you can determine what are the corresponding reducer levels at each of this point. Okay. Once I get the reducer levels at each of this point, then I can draw a graph, okay, which will give me the information of what will be the estimations of what volume of earthwork. Okay, what will be the estimations of volume of earthwork that are required. Okay, so after taking these readings, what we generally do is we'll be trying to plot a graph. We'll be trying to plot a graph on the x-axis as well as on the y-axis. On the y-axis, we'll be having the reducer levels. Here we'll be mentioning the RLs, and here we'll be mentioning the distances. So this will be 0 meters, 5 meters, 10 meters. This is 0, so this will be 1. Depending on whatever interval you have taken, based on that. Assume that this is 5 meters, first one, 10 meters, 10 meters, 20 meters, 30 meters, 40 meters, 50 meters. Okay. For each, at each distance, you'll be getting some RL values. So you'll be plotting that on the y-axis. So these are the corresponding RLs. So what happens is when you can simply join all of them using a straight line. Please don't bother about the shapes here because I'm not using mouse. So So I'll simply join all this again. So if I join like this, I'll be getting how the profile of the ground surface, natural ground surface is existing at 5 meters what, how much, what is the RL, 10 meters, what is the RL, 20 meters, what is the RL. And if I join like this, I'll be getting how the structure, existing structure of the ground surface is there. Okay, how the picture or how the profile of the existing ground surface is there. And on this, if I overlay my design RL, okay, 200 meters, I want to lay a road from the mean sea level. So this horizontal line is 200 meters, let's assume. Then what I need to do in order to lay this road, I need to excavate this top portion, right? Okay, I need to excavate this top portion. So I can do an analysis of what is going to be the volume of earthwork I need to excavate, and I can do the corresponding cost management, etc. kind of thing. Okay, that is the purpose of the profile leveling or longitudinal cross sectioning, longitudinal leveling. Okay, but along with the longitudinal leveling, we'll also be doing the cross sectional leveling, because in this figure, what this is my stretch. I'm taking. I'm taking the readings along the center line. But in order to calculate the volume, you also need this portion also, right? So for that, what we'll be doing is we'll be placing, okay, at the same 5 meter interval or 10 meter interval, whatever interval you want. What we'll be doing is we'll be taking the staff readings perpendicularly also.
Sir, 325 under join, sir.
They can join directly, right?
It is asking permission, sir.
I'm not getting any here. They can automatically join. Okay. So at cross sections. So like this, at every 5 meter or 10 meter, 50 meter, whatever you want, we'll be taking 6 readings. Okay. We'll be taking 6 readings. I'll show here only. So this is my center line. Okay. So at 90 degrees to the center line. So on the left hand side, I'll be taking 3 readings. On the right hand side also, I'll be taking the 3 readings. So at every interval, I'll be getting 7 readings. 1 on the center line, 3 on the left hand side, and 3 on the right hand side. So generally, this left hand side and right hand side intervals will be based on the width of the road. Okay. It can be 1 meter, 2 meter, 3 meter on one side, and another 1 meter, 2 meter, 3 meter on the other side, or it can vary depending on the width of the road. So what I'm doing now, I'm taking the readings along the center line. I'm also taking the readings along the perpendicular line. So I will be getting now RLs in a grid format like this, right? Okay. Completely, I'll be getting in a grid format. Once I get the staff readings, I can determine what is the RLs. Okay. Once I know the RLs, again I can plot a graph in order to do the calculations. So in the plot, what we'll be doing here is, again, this is going to be my 0 point. Okay, at 0 meters, what is the value? Okay. Similarly, towards the left hand side, let's assume that I'm taking 1, 2, 3 meters. I'm taking the readings at 1 meter, 2 meter, and 3 meters from the center. Okay. This is going to be my 2 meter from the center. This is going to be my 3 meter from the center. Similarly, this is going to be my 1 meter from the right side. Again, 1 meter, 2 meter from the right side. Then 3 meter on the right side. So again, if I try to join all these lines, I'll be getting, okay, how the profile is, how the structure of the ground is there along the perpendicular direction towards the center line. So in the first case, what I'm getting how the structure of the surface along the center line. In the second case, in the cross-sectional surveying, what I'm getting, how the structure of the ground surface is along the perpendicular direction to the center line of the alignment. Okay. Again, I can overlay this, the design RL on this, and determine whether there is going to be an excavation or there is going to be any filling of the earth, and I can do the corresponding calculations. Okay. But one thing what you need to keep in mind is whenever you are trying to draw this graph, the vertical scale has to be exaggerated. Okay? Because what will be the RL values 200, 200.1, 200.2, like that you'll be getting, because there will not be much variation. If within 10 meters, there can't be much variation of 1 meter, right? If at the starting point, if the RL is 200 meters, at 10 meters distance from that, you can't get a 210 meters, okay? Or you can't get a 201 meters. It will be, variation will be only in the form of centimeters, okay? It can't be in the form of meters, especially if at all, if it is having less than, if at all it is having a natural depression, the variation will be very less. The variation will be very less. Okay? So that is the reason why we need to we need to we need to exaggerate the vertical scale so that you'll be getting a clear picture of how the ground surface is existing. Otherwise, if you maintain the same scale on the x-axis and the y-axis, the variation will not be visible clearly. Okay, that is the purpose why we need to exaggerate the vertical scale. That is, the RL scale has to be, suppose if you are taking 0 meters on the graph sheet, one block you are taking as 5 meters or 1 meter, 2 meter. On the RL scale, on the y-axis, you need to take it as 0.5 or 0.25, one block on the graph sheet. Then you'll be able to get a clear picture. Okay, so that is the profile leveling or cross-sectional leveling. Generally, we do these two leveling experiments parallelly. We can't do it separately because we need to determine what is the volume of the earthwork, okay, involved in execution of any given civil engineering project. Okay, am I clear? And precise leveling is used for establishing benchmarks for future public use. Okay? It is carried out with high degree of accuracy using advanced instruments. So not only the leveling operations, any civil engineering surveying is completely dependent on what is the amount of accuracy you need to get. And the accuracy is completely dependent on project cost. Okay? If the project cost is 1,000 rupees or 2,000 rupees, you can't give 100% accuracy. But if the project cost is around 1,000 crores or 2,000 crores, then definitely you need to ensure at least 99.99% accuracy. Giving 100% accuracy is not at all possible. Okay, so depending on the quality of the work required, depending on the project cost, okay, depending on the purpose, you need to decide which type of leveling you need to go. Okay, increase in accuracy is directly related to increase in cost of the project. Okay, so in trigonometrical leveling, what we generally do is vertical distances between points are computed by observing horizontal distances and vertical angles between the points. You can see in this bottom figure, okay, I want to determine what is the vertical distance. I want to determine what is the height of this. Okay. So I'll be establishing my instrument at one station, at one point, and I'll be measuring the angle of this. Okay, I'll be measuring the top angle of the top point, and I'll be measuring what is the horizontal distance between the instrument position and the corresponding point. So with one angle and one distance, I can determine what is the vertical height. What is the equation I can use here? This is a triangle. This is a triangle. This is the height. This is the length distance between instrument station and point. And this is unknown to me. And this is alpha. What is the angle I can use?
Tan alpha equals to V by H.
Tan alpha is equal to opposite by adjacent is equal to V by H. So V is unknown. So vertical distance I am going to measure using trigonometrical leveling. So this is mostly useful when the object whose height is to be determined is not accessible to us, or the distance between the object and the distance is more. Okay. Okay. In those cases, we'll be generally going for trigonometric leveling. Suppose I want to measure what is the height of a building. Okay, what is the height of a building which is outside our compound? The better option is only to measure the angle of the top of the building and measure one distance between the station point and object and determine what is the height of the object. Okay, so when ground is also not supporting us for establishing of the instrument or for taking the measurements, generally we go for this trigonometrical element because the measurement of horizontal distances is reduced. In this case, what we are doing, we are measuring only one time horizontal distance. Remaining is angle. Okay, so when the ground scenario is not suitable for taking horizontal measurements, okay, and it is suitable for taking angular measurements, generally we go for trigonometrical leveling. Okay, and this is the reciprocal leveling. Okay, so in this reciprocal leveling is generally done when we don't have an access to do continuous ground surface. Okay, so this method is adopted to accurately determine the difference of level between 2 points which are far apart. It is also used when it is not possible to set up level in midway between the 2 points. Okay. You can see there is a river here, there is a small pond, and you want to determine what is the elevation difference between point A and point B, which are on either side of the pond. So general procedure is you will be establishing your instrument at some midway position and keep a staff at A and keep a staff at B, and you will take the staff readings and you will calculate the RLs. But in pond where you can keep, okay, forget, you can't keep in the between the pond. If it is not possible for us, the pond area will be generally more. So if you go to either side on the between away from the pond also, your instrument may not have the capability of reading the staff readings. Okay. In those scenarios, what we generally do is we generally go for reciprocal leveling. Okay. So here let us see, this point A is one point A and point B are 2 points on the opposite sides of the bank of a river. Okay, and we purpose is to determine what is the elevation difference between A and B. So what we'll be doing is we'll be setting up the instrument at a position which is nearer to A. Okay, we'll set up the instrument at a position which is nearer to A. Here you can see this is the instrument position, this is the point A. Okay, and you'll be taking the readings here. Okay, you'll be taking the reading at A. And you'll also be taking the reading at B. Okay? But the reading at B is subjected to error because the line of sight which is supposed to be horizontal, okay, when the line of sight which is supposed to be horizontal when the instrument is set up will not be horizontal. Okay, and the level line and the line of sight will not coincide because the effect of curvature is coming into picture here. As the distance increases from the level instrument, the effect of curvature comes into picture. Okay. So the value should be here, but the line of sight, you see, you are getting it above. So you are getting some error here. This small portion is called as your error. Okay. So you'll establish your instrument at A and you'll be taking the readings at A and B. Okay. And again, you'll be shifting your instrument to B now. You'll establish your instrument at B, nearer to the B, and you'll be taking the reading again at B and again at A. So in this case, what is happening when the system is at A, okay, the reading on A is perfect because the distance between A and the instrument position is less. You are going to get a perfect staff reading. In the second case, this reading at B is perfect, okay, but the reading at A in the second case and the reading at B is not perfect 100%. There is an impact of the angular error, or there is an impact of an error in this. Okay, so how to determine this now? Okay, how to calculate this error? Okay, and how to determine what is the difference between the two elevations is what is called as your reciprocal leveling. Okay, so this is the simple derivation for that. Okay, so let D is the true difference of level between A and B, and A is the error due to curvature, refraction, and imperfect adjustment of the instrument. Curvature effect and refraction effect will definitely be there when the distance from the instrument is increasing. Okay, because the earth is curved. Okay, so to eliminate this error, what we'll be generally doing is, okay, thus to eliminate the error, take an average of the difference in elevations taken from 2 points. That is, from A, the true difference will be B1 minus E. You can see here from A, okay, the true difference will be B1. B1 is from here to here minus C. Okay, or you can also write it as D is equal to B1 minus A1 minus C. B1 minus A1 minus C. Okay, and from B, the difference in elevation will be B2 minus A2. B2 is this one. This is correct one. Okay, minus A2 of minus C. Here what is required? this line of collimation is this error you need to add. B2 minus or A2 minus A is B2 minus A2 plus C will become. Okay. So in the first scenario, what you're doing, you're taking the difference of two staff readings, staff reading at A1, staff reading at B1, and you're subtracting the error. In the second case, what you're doing, you're taking the difference of two staff readings, staff reading B2 and staff reading A2, and you're adding the error here. Okay. And if you add these two equations, you can eliminate the value E, that is error can be eliminated. So you'll be getting, if you solve this equation, two equations by adding, you'll be getting D is equal to B1 minus A1 plus B2 minus A2 by 2. Okay. So this is the equation which is used to calculate what is the difference in elevations of 2 points which are on either side of a pond or a lake. Okay. Then the curvature and refraction corrections, you can see in this figure. Okay, as you're moving away from the distance from the instrument setup, okay, you are going to have a curvature effect. Your line of sight is this. It should be parallel. It should be straight. But what happens is the earth is descending further, you'll be getting a inclination here. That is the effect of curvature. Okay. So for long sights, the curvature of earth can affect staff readings. The line of sight is horizontal, but the level line is curved and parallel to the mean parallel surface of the earth. So actually, when the system is perfectly level, the surface is level, the level line and the line of sight should coincide. But in these scenarios, what is happening? The line of sight and the level line are not coinciding. This is the level line. The bottom one is the level line, which is parallel to the mean sea level and which is curved in nature because earth is curved. But the line of sight is always horizontal. So this effect, this difference is called as the curvature effect. Okay. So the vertical distance between the line of sight and level line at a particular place is called the curvature correction. This portion, this small portion is called as the curvature correction. Okay. So the effect of curvature is to cause the object sighted to appear lower than they really are. So what is happening? You are going to get a feeling that the object is lower than actually their position. Okay. So what we need to do? We always should do a negative correction. So what is happening now? I'm getting a lower value, right? I'm getting a staff reading of this, right? When I place my staff at this point, the line of sight is horizontal. It is bisecting the staff here. I'm getting this staff reading. But what is the RL? This is the RL because this is the level line, right? This is the level line. So I need to subtract this one in order to get the correct reading. This should be the actual staff reading at this point. Okay, this is the actual staff reading. So if you subtract this staff reading, you'll be getting the RL of this point. But my line of sight is getting bisected at this point. So I need to remove this portion in order to get the accurate RL of this point. Okay. So that is the reason why we need to always subtract the correct curvature correction. Okay. So in order to get the true staff reading, the observed staff reading minus 0.0785 d square, where d is in distance in kilometers. If you use this equation, you will be getting what is the correct staff reading, or you will be eliminating the curvature correction. You will be eliminating the curvature effect. Okay. So this is the equation that is used. Observed staff reading minus 0.0785 d square, where d is the distance between the instrument position and the staff position. This is the distance, and it should be mentioned in kilometers. Okay. And refraction also, these both are generally called as combined corrections, and definitely both will be having the impact when the distance is increasing. Okay. So the ray of light passed through layers of air of different densities and refractor bent down. The effect of refraction is to make the object appear higher than they really are. Refraction varies considerably with climatic conditions. You can see here. Okay, it is going to bend the ray when you're sighting the object because of variation in the densities. Okay, the ray is subjected to bend down. Okay, but the actual position is again this one, the straight one. Okay, so it should be added. Okay, I'm going to get this reading. I'm supposed to get a reading at this line, but I'm getting a reading at this point because of the refraction. So what I need to do, I need to add here the staff reading in order to nullify the refraction effect. Okay. So it is taken as CR is equal to 0.0112 d square meters. Okay, and it is a positive. Curvature effect is negative, refraction effect is positive. Okay. So in order to get the true staff reading, you need to add the refraction correction to the observed staff reading. Okay. So for the curvature, it is observed staff reading minus 0.0785 d square meters, and for refraction, it is observed staff reading plus 0.0112 d square meters, where d is in distance between the instrument position and the staff position, and it should be mentioned in the form of kilometers. Okay. So most of the cases we generally go for combined corrections. Okay, both will be applying both curvature correction as well as the refractive correction when the distance is increasing. Okay, am I clear till here? Any doubts still here? I'm repeating one problem for both C1 and C2. It is new, but for C1, I'm repeating another one, same problem. People who have not attended in the first class, please try to follow that. Okay. So you have already done this method of reducing levels, height of instrument method. You have already done both the sections. Okay, how to calculate the reducer level when a setup of readings are given. Okay, so in addition to this height of instrument method, we have one more method, that is rise and fall method. Okay. Okay. In this method, what we'll be doing is we'll be determining the difference of levels between consecutive points by comparing each point with immediate preceding point. Okay. In the height of instrument, what we are doing, we are calculating first the height of instrument after taking a backside. Okay. After the height of instrument is calculated, height of instrument is equal to RL of the benchmark plus backside. After calculating height of instrument, you are determining the RLs of other points by subtracting the intermediate sides and foresights from the height of instrument for a setup of readings. When the system is shifted, then again you are going to calculate new height of instrument, and again you are going to subtract intermediate sides and foresights to get the RLs of corresponding points. Okay, so in that case, if at all any mistake has occurred in the calculation of RLs, it is going unnoticed. It is going unnoticed. So in order to assure or in order to cross verify whether we are doing a correct calculations or not, then we can go for this rise and fall method, where we are going to do the subtraction or finding out the numerical difference between two successive points. Okay, so in this figure you can see there is one instrument which is established at one point, and a benchmark is 100 meters of A, and a backside is taken here of 0.9 meters. Then an intermediate site is taken at 1.1 meters, and a foresight is taken of 1.05 meters. After taking these three readings, the instrument is shifted, and again a backside was taken and a foresight is taken. In the second setup of instrument, only two readings were taken. In the first setup, three readings were taken. So the backside we are mentioning in the backside column. 1.1 is the intermediate site in the second column. 1.05 is the foresight we are mentioning in the third column. Okay, when the instrument is shifted, you will be getting the foresight and backside in the same row. So in the second backside, 1.45 meters also we are mentioning in the same foresight column, and the last foresight we are mentioning in the foresight column. So in the earlier table, we used to have station, backside, intermediate side, foresight, height of instrument, RL, and remarks. But in rise and fall method, we are having two more columns. One is rise and one is fall. Okay. So how to determine rise and fall? Okay. Simple. Rise means there is going to be an increase in the elevation of the ground surface. Fall means there is going to be a decrease in the elevation of the ground surface. So what we are going to do here is we are going to find out the difference between two successive staff readings. When a staff is placed at A, the staff reading is 0.9. When the staff is placed at B, the staff reading is 1.1 meters. So what does it indicate? When the staff reading is increasing, what does it indicate?
Rise.
Huh? When the staff reading is increasing, does it indicate rise or fall? You see in the bottom figure, this one, right one. Okay, this is one staff reading. This is second staff reading. So what will be the reading on the second one here? You'll be getting more reading, right, when compared to the first one.
Yes, sir.
But see how the ground surface is, which is elevated, which is depressed. Here the ground level is higher than this level, right? Yes or no?
Yes, sir.
So a lower staff reading indicates the ground surface is at an elevated position, and a higher staff reading indicates the ground is at a lower elevation. Please keep that point in mind. Okay. A lower staff reading indicates the ground surface is at a higher elevation. A higher staff reading indicates the ground is at a depressed position. So now what is happening? At A, the staff reading is 0.9. At B, the staff reading is 1.1. So what is happening to the ground surface?
Decreasing.
The ground surface is decreasing. So what is the numerical difference of these two? 0.9 and 1.1, it is 0.2. So we'll be mentioning that 0.2 in the fall column. The ground is falling, or the ground is reducing or decreasing. Now what are the next successive readings? 1.1 to 1.05. 1.1 to 1.05. Okay. So what is happening now here? 1.1 to 1.05, the staff reading is increasing or decreasing?
Decreasing.
Increasing, sir.
వరుణ్
చేయొచ్చు కదా క్యారెక్టరైజింగ్. ఫస్ట్ అవి కానీ వీటిన తర్వాత ఆయిల్ పోసి జీలకర్ర ఆవాలు వేసి పచ్చిమిర్చి వేగినాక నెక్స్ట్ యాడ్ ద క్యారెట్ సాల్ట్.
There was a disconnected. The call was disconnected. I'll explain you this rise and fall method again. Am I audible?
Yes, sir.
So these are the readings given. I'll explain once again. Yeah. If at all my call gets disconnected, please keep a message in WhatsApp immediately. Okay. So these are the readings given: 2.665, 3.225, 2.905, 1.85, 0.98, 2.62, 1.585, 0.96, 1.425. And we are also given information of RL of benchmark as 240 meters. Okay. So the first reading by default is the backside. So I'll be copying the first reading in the backside. The second reading is the intermediate side. Third reading is the fourth side because the instrument is shifted after the third reading. So I'm copying 2.905 in the fourth side. So the fourth reading will be the backside because after intermediates, after the fourth side, the reading taken is the backside. So 1.85 is again I'm copying in the backside. Then 0.98 is again intermediate side. 2.62 is the sixth reading. After the sixth reading, instrument is shifted, so it will become my fourth side. And next 1.585 is the next reading after taking fourth side, so it will be my back side. And 0.96 is the intermediate side. 0.425 is the last reading of the work, so it will become your fourth side. So you need to transfer these values into corresponding fourth sides, back sides, and intermediate sides. Okay. Once this is done, then I need to determine where is rise and where is fall. So in order to determine where is rise and where is fall, I need to find out what is the numerical difference between two successive readings. So what are successive readings here? A, B are successive readings. Okay. So the difference between A and B, okay, as the staff reading is increasing from A to B, it is going to indicate a fall. The ground surface is decreasing. So fall at B is equal to 2.665 minus 3.225 is equal to 0.560. I need to mention that 0.560 in the fall column. Okay. Next two successive readings are B to C. Okay. So the B staff reading is more, C staff reading is less, so it indicates a rise. So rise at C is equal to 3.225 minus 2.905. The difference is 0.320. I'm mentioning it in the rise column. Okay, from A to C, it is one setup of instrument. At C, the system is changed, instrument is changed. So again now, these two becomes the consecutive readings, successive readings. Okay. So 1.85, the rise at D is equal to 1.85 minus 0.98, 0.87 is the value I'm copying it in the rise column. Then again, these two are the successive readings, 0.98 and 2.62, intermediate side and fourth side. Okay, so the difference is again 1.60, it is decreasing. The staff reading is increasing, so it indicates the ground is decreasing. So 1.64, I'm copying it in the fall column. So again here, one setup of instrument is completed up to here. Now the last setup of instrument. So these two are successive readings now. So the staff reading is decreasing. So it is indicates a rise. So rise at F is equal to 1.585 minus 0.96. Okay, 0.65 I'm copying in the rise column. Then these two are the successive readings. The staff reading is increasing. So the difference of 0.96 minus 0.425 is equal to 0.535. I'm copying it in the rise column. Okay. So once you determine these rises and falls, then you can calculate the RLs. RL of the benchmark is already given to you 240 meters. From A to B, what is happening? The ground is falling. So what will be the RL? 240 minus 0.560, you will be getting what is the RL of B. RL of B is equal to RL of A minus fall at B. Okay. So from B to C, what is happening? The ground is rising. Okay. So the RL of C is equal to RL of B plus rise at C. 239.44 plus 0.320, you'll be getting the RL of C. From C to D, what is happening? The ground is rising. So RL of D is equal to RL of C plus rise at D. You'll be getting this value. From D to E, what is happening? The ground is falling. So RL of E is equal to RL of D minus fall at E. 240.630 minus 1.630, 634. You'll be getting this RL. From E to F, the ground is rising. Okay. So add the corresponding rise. From F to G, the ground is rising. RL of F plus rise at G. Okay. Once you calculate these RLs, you have a check. Sum of back sides minus sum of four sides is equal to sum of rise minus sum of fall equal to last RL minus first RL. Okay. If you do that, you need to get the same value. If you get the same value, you can say that the problem is correct. Okay. So in this, you need to be very careful while determining the rise and fall because the RLs are dependent on the previous, the RL of a particular point is dependent on the RL of the previous point and corresponding fall or rise. Okay, if at all any mistake is occurred here, this last RL minus first RL check may not be satisfied. So you need to be very careful while doing these problems. Okay. We'll again do it tomorrow in tomorrow offline class. Okay. Please post your attendance in the chat box,
Okay, sir.
Okay, sir.
all of you, and we'll meet tomorrow in the class, offline class. Okay. And I'll send the assignment in the WhatsApp group. Please try to solve them and try to submit before the exams. Okay.